So my name is Yongjoo, and you can find more information about myself at the website there, myname.com. So data analytics and machine learning are becoming extremely ubiquitous. It's been having massive impact on healthcare, manufacturing, retail, all sorts of industry. And as a researcher and a developer, I study problems that are core to accelerating these analytical operations. And today I'm going to talk about how we could accelerate these operations using sampling. But before I talk more details about our systems, I'm going to share a great secret that I recently discovered, which is about how to win the lottery. So this is a deal. If you want to double your chance, buy 2 tickets. If you want to triple your chance, then buy 3 tickets. In other words, you have a perfectly linear relationship between the number of tickets you buy and your chance of winning. And believe it or not, this was actual news on Fox and Friends just a couple of years ago. And this is exactly why I think you're better off buying lottery tickets than traditional data systems. This is how traditional data systems work. If you want to double the speed, then double your hardware. If you want to triple the speed, then triple your hardware. But at least with the lottery, you get linear speedups. But with a lot of these traditional data systems, you only get sublinear scalability for most part. So the way we try to address this traditional limitation of linear scalability is by making the problem easier, but at the same time harder. So we add a third dimension, which is quality or statistical properties in general. And this new dimension allows us to get superlinear scalability. To see how we can get superlinear scalability, let's take a simple example. We're trying to find out what is the average income of the United States. And from some statistical theories, we all know that after seeing a tiny fraction of the entire data, if you sample them randomly and independently, the sample mean quickly converges to the true mean. And this is the key insight behind asymptotic statistics. When we only see like 1% of data, we can still get an answer that's 99.9% accurate. And this is the whole premise of superlinear scalability. That is, by taking this quality into account, we can get superlinear scalability in data analytics. Even though this idea is pretty straightforward for this simple average case, bringing this idea inside a real data management pipeline introduces a number of challenges. The first challenge is generality, because you're dealing with much more complex forms of analytics, such as SQL queries, machine learning training, and end-to-end computation that analysts are doing. The second challenge is correctness. You want to be able to do approximation with some sort of correctness guarantees. What I always say is that your approximation is only as useful as its accuracy guarantees. If you didn't care about accuracy guarantee, then approximation would be trivial. No matter what your query is, I can come back and say your answer is 5. So in order to guarantee that, we want to know when we are wrong, if we want users to trust our system. And the final thing is ensuring the efficiency. We want to do all these things in a super efficient way. The easiest way to find out if your approximation is accurate enough is go on and take a look at the entire data and compute the ground truth. But this obviously defeats the whole purpose of doing approximation. And also, giving you a 99% accurate answer, for example, only twice faster may not be very attractive. But giving you a 99% accurate answer 200 times faster is a very compelling case in many applications. So we want to support a large class of queries with accuracy guarantees, and we want to do it in a very efficient way. And I'm going to talk about today that sampling provides a very powerful mechanisms, so in order to ensure this. So today I'm going to talk about just 3 things. First is why sampling-based approaches are so powerful and universal. And then I'm going to talk about how to apply those techniques into SQL-based analytics. And then I'm going to talk about how to apply those techniques to accelerate the machine learning workloads. So first, why are sampling-based approaches so universal? Although my discussion itself will be pretty general, I'm going to specifically focus on this very simple case. What is the average income? So the reason why the sampling-based approaches are so general is because sampling works for most data, actually. There are 2 situations. What I mean by work for most data is that sampling mean, for example, computing sample mean is mostly independent of the distribution of data if we use a reasonable sampling method. And also it is independent of the size of the data. I'm going to talk more details about that. So these properties, these very interesting properties are explained by a bunch of statistical theorems. But I'm going to focus on the one specific theorem, which is called the central limit theorem. But I'm not going to talk about any mathematical details. So first, the property I mentioned is that the sampling-based approaches are independent of the data distribution. What I mean by that? Let's say we have a data set that contains 1 billion values, for example, and then we want to know what is the mean of these values. If you visualize the values, then you can follow any of these histograms like this. but we don't have to know that what kind of histograms are actually exactly capturing this distribution of the data. Because we can apply just a single, like a same procedure for computing or estimating this mean. So we take a sample and compute the sample mean and the standard deviation, and then we can pretty much, we can not only can estimate the mean of the original data, but also we can put a tight error bound that contains the true answer with extremely high probability. And also another very interesting property is that this approach is independent of the size of the data. So let's say that this data is not 1 billion items. This data set contains 10 billion items. But the procedure I just described is pretty much the same. We can just use the same answer regardless of the size of the original data set size itself. So I've just talked about why the sampling approaches are so powerful. First was that we don't have to fully understand what's the actual distribution of the data. And the second part is that we don't have to adjust our procedures just because of the size of the data. And then I'm going to apply these interesting properties to accelerate the SQL-based analytics. So although the discussion myself, my discussion will be also pretty general, but I'm going to specifically focus on computing this select average SQL query. So why is sampling useful in the first place when we are using the sampling technique on computer systems actually? So let's say that like, if our table contains 1 billion tuples. This table can be any of these, for example, like a pandas data frame or the Spark dataset or just the relational database tables. We pre-generate the sample out of this table, and then once we construct this sample, we can just use this sample again and again, whatever queries are coming. For example, let's say that you want to compute the average price, and then we can just compute the answer using the sample. And then we can estimate the original answer using based on the sample-based answer. Let's say that there's another queries with a different like a column values and another filtering conditions. We don't have to use the original table again. We can just use the sample table to answer the original question again and again. So that's the reason why we can save both the I/O cost and the computation costs. And then this is how the traditional Approximate SQL systems work. So user submits some analytic query to the Approximate SQL system. Then the system determines if this query can be approximated using a tiny fraction of the data. If it can be approximated, then it returns an approximate answer along with the error bound. Let's say it took this amount of time for computing this approximate answer. If you allow more time for the system, then it returns a more accurate answer. If you decide it's worth waiting for full computation, then you can also get an exact answer as well. So if you look at the academic research papers, though, there is a long history of this approximate query processing. So if you on the slide, you can show that it's been more than 30 years since the first work on approximate counting estimator was published. And the paper shown in this slide is a tiny fraction of the all approximate query processing related publications. But despite this long history, the industry adoption of these techniques has been pretty limited. Our hypothesis behind this slow adoption is that these AQP, or the approximate query processing techniques, typically require deep modifications of the existing database systems. So traditional database vendors, such as Microsoft SQL, with stable code base, are reluctant to adapt these major changes, especially when they have millions of existing customers. The situation could be better for newer SQL-owned Hadoop communities, but they have a lot of other stuff in their hands in terms of implementing standard features. And also, users are not going to just abandon their existing systems in order to use a research prototype, especially when they have billions of data set in their existing database systems. And also some notions that are related to approximate answers, such as confidence bound or the error bound, makes it harder to understand. So at Michigan, we started to develop the systems that are much easier to adapt and much easier to understand. And in this talk, I'm going to talk about how we could develop a system that is much easier to adapt. So this is our proposal, which is called the VerdictDB. So we place a thin layer, approximate layer, between the user and the regular SQL database engine. User just submits a regular SQL query, and this thin layer rewrites this query in a way that it looks like any other innocent-looking SQL query to the backend database system. But the standard execution of this rewritten query provides us enough information for us to compute approximate answers as well as error bounds. The nice thing about this architecture is that it is completely independent of the choice of this SQL engine. So basically, you can plug in whatever your favorite SQL database is in that place. So we call this entire idea Universal Approximate SQL System. For these systems to be useful, though, it must satisfy 3 requirements. It should support a large class of SQL queries. Also, it must provide a statistically correct error bound. And also, its performance should be very efficient, highly efficient. So one of the challenges we had to overcome in terms of, in the process of developing this verdict DB is this. The SQL engine has the original table and the materialized sample table. And the user submits a query. He or she wants to compute some aggregate, for example, what's the average price on the original table. And we do some processing by doing some like a query writing. And then we compute an answer using the sample table instead. By using the sample table, we can reduce the I/O cost and the computation cost and return the answer much more quickly. But the core question is, what is the difference between the quantity that could have been computed using the original table and the quantity that is actually computed using the sample table? So this is the core question. So verdict DB automatically handles the question, but the reason why it's challenging to answer the question is because we are not only interested in answering these like a simple queries, but also we are interested in answering these complex real-world queries. And verdict DB handles that. So what types of queries can verdict DB support then? So let's say you perform some transformation of your table by performing some joins and projections and selections. And if you want to compute the aggregate, for example, that includes most of the commonly used aggregate functions, then verdict DB can support those operations. And these commonly used aggregate functions covers 96% of the benchmark queries. So this is a speed that we could achieve by using verdict DB on top of regular database systems. So we are comparing the latency and showing the speedups on top of the Amazon Redshift and Spark SQL and the Cloudera Impala. And you can see that without making any modifications to those existing systems, we are delivering a huge amount of speedups. And let me show you an example of analyzing 150 gig of data using our system, verdict DB, on top of Facebook Presto. In this case, verdict DB is running on top of Facebook Presto and the Google Cloud Platform, and the regular query takes about 5 to 10 minutes on this cluster. But you can see that by using verdict DB, each query takes only like 3 seconds. So in this part, I've talked about how to apply these sampling-based approaches to accelerate the SQL-based analytics. And then in the next part, I'm going to talk about how to accelerate this machine learning training using sampling-based approaches. So in this slide, in this part, I'm going to specifically focus on training logistic regression classifiers faster. So one example task using a logistic regression classifier is sentiment analysis. Given a tweet, for example, I watched the end game, I loved it, and then we want to classify it into either positive sentiment or the negative sentiment. Then how can you train this logistic regression classifier? So typical workflow is like this. So we have some ML trainer, which is, for example, scikit-learn fit function, or if you're more advanced users, then you can use SciPy's optimized function as well. And you feed a bunch of training data set, pairs of the tweets and labeled class labels. And then this ML trainer returns the output to this trained logistic regression classifier. But the one downside of using this approach is that if the size of the training set increases, then training time typically takes more. And another problem is that typically you want to train the same classifier multiple times using different feature sets. So for example, you first try this kind of feature set by treating every different words as a distinctive features. For example, watched and watch are different features in this case. And then you train a classifier. But you didn't like the accuracy of this classifier, so you want to try a different set of features. Now you apply the stammer to treat the watched and watch into the same word and like into the same word. And you train another classifier. And you repeat this process again and again until you have like a satisfied accuracy level. There are some related problems, but different problems that are used to accelerate this processing. One particular problem is something called hyperparameter tuning, automatic hyperparameter tuning. And these types of work automatically search for example, like what's the optimal regression coefficient that can maximize the accuracy. And there's another type of work, another line of work that is called AutoML. And this AutoML work automatically generates a feature set for you so that you can try different feature sets until you have a high accuracy. But the type of problem we are trying to address in this particular topic is that can you actually speed up the ML trainer itself using sampling-based approaches? So our intuition is pretty straightforward though. If we use a sampling then have a smaller training set, then ML trainer will train this classifier more faster because we have a smaller set of training sets. But instead we get an approximate logistic regression classifier in comparison to the full exact logistic regression classifier. So the natural question is, what's the similarity between this approximate classifier and the exact original full classifier? we want to minimize the similarity, we want to maximize the similarity between these two classifiers. So our intuition is that if we use a larger training set, of course, we will get more accurate one or more similar ones. But in order to answer this question more formally, we have to answer two questions. The first question is how to formally express the similarity between the approximate trainer, approximate classifier, and the full exact classifier. And the second question is what's the minimal sample size that is still large enough to guarantee high similarity. So I'm going to answer these two questions. So the first, in order to formally express the similarity between these two classifiers, I'm going to introduce a concept we call consistency. So given a tweet, the exact classifier, the approximate classifier, both produce these class labels, positive and positive. In this case, because these are consistent, I'm going to put down 1. We feed another tweet, and then it's going to produce different class label predictions in this case, positive and negative. In this case, I write down 0. And I repeat this process multiple times. In this particular example, the consistency between the logistic regression classifier, the original one, and our approximate classifier is 75%. And then we want to figure out what's the minimum sample size that can ensure high consistency, that, for example, 90% or 99% between the approximate classifier and the exact full classifier. So we developed a system called BlinkML in order to handle this process basically. So you set the BlinkML at the consistency level, for example, 99%, and then you provide a training set. Then this BlinkML automatically figures out what's the minimum sample size that is large enough to still guarantee this required 99% consistency level. And then something very important here is that we never train the exact logistic regression classifier. In order to achieve that, BlinkML has like some two-step workflow. The first step is profiling step, and the second step is the actual training stage. In the profiling step, we use a tiny fraction of the original training data. And when we figure out the property of the statistical property of the classifier, and second, we figure out the statistical property of the data distribution or the variance of data. And by figuring out these statistical properties, we can automatically figure out what's the minimum sample size that is still large enough to guarantee the high consistency. And then we simply train the model using that sample size. So for training, in our implementation, we actually use the off-the-shelf trainer, for example, SciPy, and in the combination of the NumPy and PySpark for distributed computation. So this is the speed that we could achieve. We actually used the criteria data set for this particular experimental logistic regression, 46 million examples. And then you can see that for different levels of requested consistency levels, we could provide a large amount of speedups while still we are ensuring that the approximate models trained by our systems are actually satisfying the requested consistency levels. So this is the summary. I just talked about 3 things in today's talk. The first is I talked about why these sampling-based techniques are so universal in general. And then I have applied these ideas to accelerate the SQL-based analytical processing. And then I've talked about how we can apply this idea to accelerate the machine learning workload training. So my last thing is that we actually open sourced our VerdictDB project. And VerdictDB is currently under the open source, it's open source under the Apache license 2.0. And we are going to soon have a startup based on this. So if you're a good developer, then we can hire you, of course. And if you're an investor then, and you want to grow your asset, then let us know. And if you're any other person who are interested in a system for big data or large-scale data analytics, then I'm really interested in talking with you. So this is all. Thank you.